Hi, and welcome to week 8. This week we're going to talk about integers. We're going to be talking about integers in real life, operations on integers, zero pairs, adding and subtracting, models for integers, integer multiplication and division, on a number line and chips, and the rules for exponents. Before we get started, why don't we try to warm up from last week? Write an example of the commutative property of multiplication. Make sure you can explain how it shows the commutative property. Then I want you to think about, what do you remember about integers? What are they? And can you think of when in real life we use integers? Here's an example of the commutative property of multiplication. 28 times 3 equals 3 times 28. This shows the commutative property because the order of the factors changes, but the product stays the same. So what are integers? Integers are all the whole numbers, and now we're going to consider their opposites or negatives as well. So integers are all positive whole numbers and their opposites and 0. The numbers to the left of 0 are negative, and we denote the negative number by putting that dash symbol in front of it. Can you think of any examples in real life where we use negative numbers? Think of at least 2 examples before moving on. Here are some. The temperature in Alaska is negative 23 degrees Fahrenheit. The depth of the ocean off the coast of Florida is negative 575 feet relative to sea level. And the third one, which we might all be too familiar with, a bank account has a balance of negative $30. You have a video assignment on Canvas about Introduction to Integers, so you could do that at any point. Representing integers on a number line is very important. We could plot negative numbers that correspond to given situations. You're going to put a dot on the number line to mark the correct quantity. Also label all the surrounding tick marks. Make sure you always include 0 on your number line and scale the tick marks appropriately. So how would we show on a number line Angela lost 4 pounds? Well, if we labeled all those tick marks, we would go 4 units to the left because we're counting by ones, and we would put a dot on the number line, which is marked negative 4. We could show Laura spent $60 on her debit card, and Akara snorkeled 40 feet below the surface of the water. Think about how you would do those on a number line. All right, in these cases, I had to count by 20, so my interval size is 20 to fit it on the number line. So the first one, Laura spent $60 on her debit card. I went 3 tick marks to the left because that would be 20, 40, 60, and it's negative, so it's to the left of 0, and I put a dot on the number line. On the second one, I only had to go 2 tick marks to the left because I'm still going by 20s. I put a dot on the number line, and it's at negative 40. So what are opposites? Here's the definition for you. The opposite of a non-zero number is the number that has the same absolute value of the number but does not equal the number. So 4 is the opposite of negative 4. Negative 4 is the opposite of 4. Another useful way to think of is to add another negative sign to the number. So the opposite of 4 is, you can see how we have a negative sign or a dash in front of it, and we say equals negative 4. The opposite of negative 4, notice we put another symbol right out front, and so we would read that as the opposite of negative 4 is positive 4. Absolute value. Absolute value, it's important to understand when to use the appropriate vocabulary and the difference between them. So do you remember what absolute value means? Is it the same as opposite? It is not. Opposite means it has the same absolute value, but it's got a different sign. Absolute value means it's the distance away from 0 on a number line. And we use those straight lines up and down to show absolute value. So you can try to figure out the absolute value of negative 8, the absolute value of 8, and that last one we would read as the opposite of the absolute value of negative 8. So remember, absolute value is showing distance from 0, and distance we measure in positive values. So try those and then move on. Did you get them all right? So the absolute value of -8 and +8 is the same. It's 8, and that's because they're both 8 units from 0. The third one is the opposite of the absolute value of -8. So first you find the absolute value of -8, which is the distance -8 is from 0 on a number line. So that would be +8. But then the symbol out front says, oh, take the opposite of that. So the opposite of +8 is -8. Showing things on a number line is very helpful to our visual learners. So first, we would plot the number 5 on a number line, and then notice that I've labeled 0 with a reflection line. So opposites are the same distance from 0. So if I folded this number line on that line of reflection, the number and its opposite would touch each other. So try that, and you might see that the opposite of +5 is -5 because they're same distance from 0 on the number line. Try it again with -3. So the opposite of -3 is +3, and you can see right here that they're the same distance from 0 on the number line. All right, moving on to chip representations. All right, so colored chips are a great way to represent positives and negatives. So one yellow chip will be +1 and one red chip will be -1. So what numbers are represented in those pictures below? Now, you don't want to say an addition sentence or a subtraction sentence, you just want to say the value that's being shown there. So think about that for a minute and then keep going and you'll see if you were correct. All right, so A was +5 because there were 5 yellow chips. B was -3 because there were 3 red chips. Now on part C and part D, you might have had to think a little bit more. Every time you have a red chip and a yellow chip, they have a value of 0. They're called a 0 pair. So in part C, there's 1 0 pair, and then there's 2 red chips. So the value of C is -2. And on D, this time we have 2 0 pairs. So we have 2 yellow chips and 2 red chips, which have a value of 0. And so there's 1 yellow chip left over, so that's a value of +1. So now I want you to use a virtual manipulative, or if you have some colored chips at home, you could use them, or you could just draw it on a piece of paper. So how would you show a +3? Well, you'd put out 3 yellow chips. Now, how would you show a +3 using more than 3 yellow chips? Well, you can use that idea that we just talked about of 0 pairs because that won't change the value. Now you try the next two where you're going to show -5 and then you're going to show -5 in a different way. After you're done with that, look at the next part of the video and see if you were correct. All right, so we went over number 1 and number 2. Notice that's only one option of how you could show +3 using more than 3 yellow chips. I just used 2 0 pairs. You could have used 1 0 pair, or you could have used as many 0 pairs as you want. And then -5 you would show with 5 red chips. And then to show -5 in a different way, as long as you add 0 pairs, you're really showing -5 as a value. So comparing integers on a number line, if you plot 2 numbers on a number line, the one that is further in which direction is larger? And if we plot 2 numbers on a number line, the one that is further in which direction is smaller? So think about those and see what word would fit in those blanks. All right, so if you plot 2 numbers on a number line, the one that is further to the right is larger. And if you plot 2 numbers on a number line, the one that is further left is smaller. It's nice to have those rules that work all the time, so it doesn't matter if both numbers are positive, both numbers are negative, or one is positive and one. The language and notation of integers. So the plus symbol, in the past we've used that symbol to denote addition, but now we have positive and negative numbers, so now we could use it in front of a number so we know that it's positive 4. So we're going to make an agreement that we're going to only use the word plus when we're using the operation of addition, and we're going to use positive when we refer to the sign of the number. It is important to note that we don't always use the plus sign to denote a positive number. In most cases, we just leave it off and we just write 4, but it means positive 4. That other symbol, the dash or the minus sign, we have used it to denote subtraction. But now it can also mean a negative number, such as negative 4. Or it could mean the opposite of a number, so we could read it as the opposite of 8. Or if there's 2 of them, we could read it as the opposite of negative 5. So we're going to make an agreement to only use the word minus when we're referring to the operation of subtraction. And we'll use negative or opposite when it is appropriate. So the language and notation of integers is very important. You have an assignment on Canvas called the language of integers, and after we go over this little section, you can do that part of the Canvas work. So if you see this number or expression, how would you say it out loud, or how would you write it in words? If you said negative 6, you would be correct. We don't want to say minus 6. Remember, we only want to use minus when we're doing subtraction. It's going to help with our conceptual understanding of subtraction and integers in general. Here's another one. How would you write or say this one? If you said the opposite of negative 6, you would be correct. And one more, how would you say or write this one? If you said the opposite of the absolute value of 9, you would be correct. So now you could go finish that language of integers assignment. Here's just some food for thought, and you're going to do another Canvas assignment with videos on the word cancel. Should we avoid the use of the word cancel, and why? Are there occasions when we use this word cancel, and could it cause confusion in students' understanding? Put yourself in the student's situation. Cancel sometimes gives us a 0 and sometimes gives us a 1. What magic is happening here, and how do I not see it on my paper? This is really important for students' understanding. If you look at the first one, we have a division problem, 3 divided by 3, or 3 over 3, however you want to read that. And sometimes people say the 3's cancel, and we end up with 1. In the second scenario, we have an addition problem, and we say negative 7 plus 7, and some people say the negative 7 and the positive 7 cancel and end up with 0. This is problematic for student understanding. We need to be precise in our vocabulary so we help our students understand the mathematics. All right, so we have those colored chips again. So remember, a red chip is negative 1 and a yellow chip is positive 1. Let's do some addition. So the chip model with addition, it's combining or joining like we did with whole numbers. And notice here we have 5 plus 2. Those are both positive numbers, so this could have been under whole number addition. So we're going to follow similar steps. So step 1, model both addends. So I modeled the first addend with 5 yellow chips and the second addend with 2 yellow chips. Now I'm going to join or combine these together since it's addition, and then I'm going to count the chips. So we have 7 yellow chips because 5 plus 2 is 7. What if both our addends are negative? We follow the same procedure. So we're going to model both addends, 5 red chips for negative 5 and 2 red chips for negative 2. We're going to combine the chips and count them. So negative 5 plus negative 2 is negative 7. But what if we have a positive first addend and a negative second addend, we still follow the same procedure. The first addend, we model 5 yellow chips because it's a positive 5. Then we're going to model the second addend, which is 2 red chips because it's negative 2. We're going to join these together. Now you'll want to simplify this by eliminating 0 pairs. Notice I have 2 red chips and 2 yellow chips, which would each have a value of 0, because a red and a yellow together is a 0 pair. So I'm going to eliminate them, and I'm just going to count the remaining chips. So now I have 3 yellow chips, so my answer to 5 plus negative 2 must be positive 3. Make sure you're following along with chips and doing them. If you had little pieces of paper, it might help you, because when we get to subtraction, it can be a little more challenging. Here's another addition one. This time the first addend is negative and the second addend is positive. So again, we're going to model both addends. So a negative 5 is 5 red chips. A positive 2 is 2 yellow chips. I'm going to join the addends together since it's addition. I'm going to simplify by eliminating the 0 pairs. This time I end up with 3 red chips. So I must have an answer of negative 3. So negative 5 plus 2 is negative 3. This is helpful for students because they start picturing the chips in their head and they move away from this concrete model, and they can say, oh, I have more red chips than yellow chips, so I know my answer is negative. What about subtraction? We talked about subtraction before in whole numbers, and we talked about how would we describe subtraction. Instead of just saying minus, what do we want to say for the meaning? Well, in whole numbers, we use subtraction as takeaway. We're going to do the same with our model of integers. So we have 5, take away 2. Remember, with subtraction, we only model the minuend. So we're modeling the minuend of 5 yellow chips. We want to take away 2 yellow chips because remember, that 2 is positive, right? It's positive 5 minus positive 2. So we have 2 yellow chips to take away, so we take away the 2 yellow chips. We're left with 3 yellow chips, so our answer to 5 minus 2 must be positive 3. What if we have negatives? So we have a negative 5 as our minuend, so I model that. Now I want to take away negative 2. That's fine because I have 2 red or negative chips that I can take away. So I take those away, and I'm left with 3 red chips. So negative 5 minus negative 2 must be negative 3. Some of you have an algorithm or a procedure that you're used to that you feel comfortable with, and you can check and make sure that that's still the correct answer. All right, so 5 take away negative 2. So first I'm going to model the minuend. I want to take away 2 red chips, but I don't have any red chips to take away. So what can I do? Well, I can add 0 pairs like we did at the very beginning of integers, because I know if I add 0 pairs, I haven't changed the value of that positive 5. So I added 2 0 pairs, so I would have 2 red chips to take away. Now I can take away 2 red chips, and I'm going to count the remaining chips. We have 7 yellow chips remaining. So 5 take away negative 2 is actually positive 7. This is a great way to connect to the algorithm that you might already know. What if I have negative 5 take away 2? First, I'm going to model the minuend of negative 5 with 5 red chips. Now I want to take away positive 2, which is 2 yellow chips. Please remind yourself that that is a positive 2, okay? Because the subtraction sign is in front of it. That's an operation. So I need to add some 0 pairs, so I have 2 yellow chips to take away. I add 2 0 pairs. Now I can take away the 2 yellow chips, and I'm going to count the remaining chips. So I have negative 5. So I have negative 5 minus 2 equals negative 7. the number line model. We can also show this information on the number line. Some students prefer the chips, some students like the number line. It's good to show both of them. So here's 4 addition problems with the different scenarios we have. We have a positive in both our addends, then we have a negative in both our addends, then we have our first addend is positive, our second addend is negative, and then we reverse that for number 4. So remember, when you think of these, you're thinking of joining these together. Some teachers say, oh, if I have a negative, I'm going to go to the left on the number line. If I have a positive, I'm going to go to the right on the number line. So for the first one, you could model, I always start at 0, and then I model my first addend. So I would go from 0 to 5 to show that positive 5. And then since I'm adding 2, I'm going to go to the right 2 more to show 5 plus 2, and I'm going to end up at positive 7. Try those next 3, and then move on and see if you modeled them the same as I did on the next part. All right, is this how you showed it? Now, when you did 5 plus negative 2, I modeled the 0 to 5 for the positive 5. When I showed the plus negative 2, normally the plus sign would tell me I'm going to the right, but since it's a negative 2, that says I need to go back to the left. How about with subtraction? Try the same thing. Now, I have heard teachers explain it to students in that whenever you see this sign, whether it's a minus or a negative, you want to go in the opposite direction on the number line. So turn around, in other words. So for 5 minus 2, I model 5, and then I turn around because I want to go to the left and take away 2. On the second one, I would start in the direction of the left because it's negative 5. So I would model the negative 5, and then I would turn around, but then I would turn around again. So it gets a little bit confusing here unless you change it to addition like your standard algorithm does. So try showing these on a number line and see how you do. All right, did you get those answers? Think through the chip model versus the algorithm versus the number line and see what makes most sense to you. All right, the last thing I want to discuss is the return the sweater scenario. You have an adding and subtracting integers homework packet that you're going to do, and I would like you to do it with no calculator, because I want to see, just like you would have your elementary students do it, because they wouldn't have access to a calculator when they're first learning integers. You can check all your answers with the calculator so you make sure you get all the answers correct, but you should do that in a different color so it reminds yourself of what you did wrong. I won't take off points, but I want you to be aware of where you're making mistakes when you don't have a calculator. The other thing is, show as much work as you possibly can. I know a lot of you can do these in your head, but you'll want your students to explain their thinking. So if you can't show a lot of work, please explain your thinking so then we can know how you are able to explain your mathematics, which is what you'll want your students to do. So one of the hardest things for students to understand is subtracting a negative. So if you have a checking account or a debit account, students might understand this a little bit better. So you bought a sweater for $50. After that purchase, you have $150 in your checking account. You return the sweater, it doesn't match your eyes after all, to the store. Here are 2 ways to represent the return of the sweater numerically. Way 1 is the $150 balance, and you're taking away the $50 charge, okay, or the $50 debit. Now, if you think of that, taking away the $50 debit, right, or getting rid of that $50 debit is actually going to increase your balance by $50. Way B still has the $150 as the starting point, but now it just says I'm adding $50. Notice both scenarios add $50 to the account. If you think of the second way, $150, you go to the store, you bring the sweater back, they give you $50 cash, right? So that's increasing that. Whereas the other way, it might happen behind the scenes. They, eliminate that $50 debit. So this is how you can connect subtraction and addition. So you've probably been taught you can change all subtracting integers problem to adding the opposite. So in the way 1, we were subtracting a negative 50. And in the second way, way B, we change the subtraction to addition, and we take the opposite of the negative 50 and make it positive 50. So there is part of your assignment talks about that return of the sweater scenario. All right, we're not done with week 8, but we have covered a lot, especially with addition and subtraction, as well as just integers and chips. You can do all those assignments right now. Take a break here, and then come back and we'll do part 2, which is multiplication and division. See you in a while. Is negative.